Welcome, everyone. I'm Lauren Ross, the Manager of Engineering and Research at the American Wood Council, and I serve on multiple ASHRAE committees, both for residential and commercial. And we're going to be talking today about meeting residential energy requirements with wood frame construction, specifically for the 2012 IECC. This presentation is copyrighted. Here's some AIA information about this presentation. Here's our first polling question. You'll note that this is typical for our polling questions. It's more to gather information about you and what you think than anything else. It's not going to affect your participation score in any way, shape, or form.
All right, go ahead and vote. Many of you have already started. I usually give you about maybe 30 seconds to a minute to finish these, or 80%. This one's very, very easy, so go ahead, and I'm going to go ahead and close it, and then I'll share the answers. All right, so we've got about 50% engineers, 32% code officials, 11% architects, and just a smattering of building designers and others. So.
Well, good. I'm glad to see that there's some code officials out there. That hopefully this will be beneficial for them too. Okay, these are the learning objectives as stated in the description. But this is basically the outline just that follows right from the learning objective. So we're going to start very simple with R values and U factors. What are they? How to go from one to the other. And then we're going to talk about the compliance paths within the IRC and IECC and what trade-offs there are in that. Throughout the presentation, we'll be doing some example problems and talking about design aids the AWC has for doing these problems. And at the end, if we have time, we'll take some questions. Okay. So, jumping right in, R value versus U factor. So an R value is the measure of resistance to heat flow. So it's literally measuring the resistance. Okay. And it's material or product specific. So like in this picture right here, this product is showing an R30 resistance, okay? And that's usually what you're typically used to seeing is a band of insulation with a certain R value. But materials have resistances too. For example, wood has a typical resistance of 1.25 R per inch of thickness. And they're either labeled on the product or they're in the ASHRAE Handbook of Fundamentals. What's nice about the R value is it can be summed. Resistances can be summed. So if I put one insulation layer on top of another insulation layer, those R values get summed up. So since the heat has to flow through one resistance to another resistance, it's an additive effect. U factor is kind of the inverse of the R value. It's a measure of the heat flow, so it's how much heat flows through it. And it's more assembly specific. So you might be used to seeing it on like a window. So a window will have a U factor of, for example, in this case, 0.35. Now that is for the assembly of the window. Okay. And they're also often used for assemblies of entire walls or floors or something like that. And they're derived from the sum of R values. And you can't just sum U values as easily as you can R values. They're more area weighted averages than R values are. Okay? So for doing wood construction, we use what's called the parallel path method. There are other methods that can be used that are more complex, but since wood itself is a fairly decent insulator material, you're allowed to use the parallel path method according to ASHRAE Handbook of Fundamentals. So when you're trying to convert R values to U factors to try to get the U factor for this entire assembly, for this wall, for example. What you do is you get the R value for all the different components. So we have an air film, which is kind of the outside air film, and then we have, or this one's the inside, and then gypsum, stud, insulation, OSB, vinyl siding, and another air film. And we say, what path is it in? Because some of the heat is going to go through the stud, and some of the heat is going to go through the cavity or the insulation. And what you do is you say, okay, I sum the R values in each of those paths. So for the stud path, I sum up all the ones that the heat would have to go through. So it doesn't go through the insulation, but it does go through the stud, and its R value sum is just about R7. For the cavity, it doesn't go through the stud, but it does go through the insulation. So its R value sum is about 15.6, okay? And then I find the U factor for that path. Now the U factor for that path is just the inverse of the summed R value. So 6.995 inverted is 0.143. 15.62 is 0.064. Now, what I'm going to do with that is I can't just add those U factors. That's the heat flow through each one of those paths. I have to say how much area is stud or wood, how much area is that wood path, and how much area is the cavity path. And that gets what's into called the framing factor. Okay? So here we have a wall. The framing factor by definition is the projected area of wood divided by the total projected opaque area of the wall. So it's just the opaque area. So all these windows and things like that, they don't count in the denominator. Okay? Now, a framing factor is based largely upon a study that ASHRAE did that surveyed typical construction. And they found that headers come up with to be about 3 to 4%. If you're doing studs 16 inches on center, they're 21 to 22%. Studs 24 inches on center, 18 to 19%. So if you add say headers plus studs 16 inches on center, you come up with the default framing factor of 25%, and that's pretty standard for what you use. If you use studs at 24 inches on center, you come up with a default framing factor of about 22%. And that's, again, another pretty standard number that's used. So here's another poll question. This is more to see if you're paying attention than anything else. What is the definition of framing factor?
All right, so is it projected wood area, projected wall, opaque wall area, or B, projected wood area, total wall area, or C, 25% for all buildings, or D, other?
Yeah, so that's projected wall area divided by projected opaque wall area is A. B, projected wood area divided by total wall area. C, 25% for all buildings, or D, something else, other.
All right, I'm going to give you about 10 more seconds. And I'm going to close. And we've got about 69% say A, projected wood area divided by projected opaque wall area. 28% say projected wood area divided by total wall area, and just a smattering for the other two answers. All right, and okay. Lauren, tell us what the real answer is, please.
So the real answer, according to ASHRAE, is A, because it's only about the opaque wall area. That's all they care about. If you do a ResNet or HERS index, something along those lines, then your definition is B. There's a difference between how ASHRAE defines it and how HERS defines it, or ResNet defines it. And that's the difference, is between A and B. And C is a fairly decent answer in that that's kind of your default value if you're using 16 inch on center studs. So truth is all the answers are okay, but the answer I was hoping that you would guess was A, because that's how I emphasized it in this presentation. Okay, so going back to our example, okay, so we have the U factors for going through the stud path, and we have U factors going through the cavity path, okay? And from the framing factor, we're just going to assume it's 25%, okay? 16 inches on center, normal headers. So we say, look, 25% is going through the studs, 75% is going through the cavity. We just take the U factor of the studs, multiply it by 0.25, or 25%, add then the 0.064 and multiply that by 0.75. 75% is going through the cavity. And we add those two together and we get an overall U factor of the assembly, 0.084. Okay, so there's certain numbers that I'd like you guys to remember during this presentation, and this is one of them, 0.084. So this was a R13 wall with 2x4 studs, okay? 2x4 studs, R13 wall, and that has a U factor of 0.084, okay? So remember 0.084 for me during the presentation. We'll come back to it, okay? There's just showing the math right there of how we got to 0.4. Wouldn't it be nice if you didn't have to do all that math? That's one of the design aids that we came up with. This is a table out of DCA7. And this is showing, hey, look, wood 16 inches on center with interior sheathing, exterior sheathing, and look, if you're using vinyl siding, 2x4 R13, look, there's our 0.084. It just gives it to you. So you don't have to do all the calculations. And that's one of the design aids that we have. And we'll talk more about DCA7 in a bit. But we wanted to give you something that made it so that you don't have to do the calculations. So now we're talking about the compliance paths. Now the same options are in the IRC and the IECC, okay? They were made to align in the 2012 version. This was kind of new to the 2012 version, and it will continue, as I foresee it will continue to go that way. They made it so that there's really no distinction between the two. And so when we're talking about, if I say IECC, it's just as applicable for the IRC. So whatever energy provisions your local jurisdiction's adopting or whatever it may be, then those are it. So we're talking either Part 4 energy conservation of the IRC or the residential provisions of IECC chapters 1 through 5. Okay. There's 3 prescriptive compliance paths. There's also a performance path, but that requires more intense modeling, and so it's kind of outside the scope of this presentation. But the 3 prescriptive paths are the R value path, which is very simple, and it's cavity or cavity and continuous insulation focus. So just as long as you have enough insulation in there, you're fine. It just says, I don't care about anything else, just put enough insulation in. It's the least flexible though. If you do anything that's out of the ordinary, you're stuck. You probably can't use that table. The U factor method is similar to the R value in that it's a table-based methodology. So, but it's assembly-based, so it's a performance-based. It says, look, your assembly has to meet this requirement. Instead of saying your insulation has to meet the requirement, it's the overall assembly of the wall or the roof or whatever it is has to perform at this. So you can trade off parts within the assembly. If you're using like a structural insulated panel, this might be a good way to go because it's not going to be in the R value table for a structurally insulated panel, but your overall assembly might be equal to or better than whatever is in the R value table, and so you can say, look, through U factor, I'm equivalent. The total UA methodology is the most complex of the prescriptive paths. It allows trade-offs between assemblies. So it says, look, I don't need to have quite as good of walls if I beef up my roof, for example. And it's the method that's used by DCA7 and ResCheck. And we'll talk about those both in a little bit. But it's the most complex and most flexible of all the prescriptive methods. So the R value compliance path. It's pretty straightforward. All you have to do is know your climate zone when there's a map at the beginning of the IECC, and it has the counties and things on it. And so you pick out your climate zone, and then, for example, your wood, if you're doing a wall, you just say, look, this is how much insulation I need. So for our example, that was the R13 2x4 wall, it's compliant in climate zones 1 and 2. Now you'll notice that it doesn't actually say whether you need a 2x4 or 2x6 on there. It's just kind of an assumed information there that you're not going to try to put R20 into a 2x4. Okay. You'll also notice that the fenestrations are labeled in U factors because they're assembly, and that there's no requirement in climate zone 1. Okay. Also, in the R value tables, that's this famous footnote H. Okay. This is the 2012 IECC, and there's footnote H is literally what's just on the screen right there, but there's two parts to footnote H. Okay. The first one describes what it means if it says like 13 plus 5 or 20 plus 5 or 13 plus 10. The first part, the 13 or the 20, is the cavity insulation. So that's the bat insulation or whatever. It's the cavity part. The plus whatever is the continuous insulation that's on the outside or wherever you put it. Okay. So that's the first part of footnote H. The second part of footnote H is this: if structural sheathing covers 40% or less of the exterior, continuous insulation R value shall be permitted to be reduced by no more than R3 in locations where structural sheathing is used to maintain a consistent total sheathing thickness. So you're actually allowed to decrease the continuous insulation a little bit if you've got some structural sheathing to make it so you get a nice flush wall. Now that second part was actually moved into the main text in the 2015 IECC, but it's still there. So the U factor path, this is the main table for the U factor path. It's pretty similar to the R value path. You get your climate zone, and then you say, look, this is what I need for my wall, for example. Okay? So then you have to do your calculation for your U value and check it out. So what this basically says is, look, if I have two different walls, this is my base wall, and if I have two different walls, say I'm using insulated siding or whatever it is, and as long as it's equivalent, it's okay. It's the energy performance. Okay, as long as it has the same U factor, I'm okay. And you'll also notice that the fenestration values are a little bit different in this one because we've got a 0.5 U factor in climate zone 1. And that's because for the U factor table is also used in the UA alternative method and for the performance method. So they had to give a value here for what the base assumptions are. Now, here's kind of an interesting thing with the 2012 IECC. If you notice, we said in the R value table that an R13 wall would work. And we calculated in our first example that U factor was 0.084. But now we look at the frame walls, and they require a 0.082. Now, U factors are maximums because they're the amount of heat flow that can go through the assembly. So since our calculated value of 0.084 is larger than 0.082, it's non-compliant. It doesn't work. So we were allowed in the R value tables, but if you did the calculations for the U factor tables, it doesn't work. Which brings us to the next poll question, which is kind of more of, I'm interested in what you're saying. So, is a 2x4 wall, R13 wall, compliant in climate zones 1 and 2 with the 2012 IECC?
Okay, so your choices are A, yes, but only using the R value path, or B, no, its U factor is too high, C, whatever res check says, or D, all of the above. Go ahead and vote. About 15 more seconds. And I'm going to go ahead and close the poll and share it. All right, so about 50% say yes, but only using the R value path. 20% say no, the U factor is too high. 28% say all of the above, and just a couple say whatever res check says. And Lauren?
Yeah, this one's kind of a hard one to answer because they're all kind of right in what they do, and it's really based upon the assumptions that you make, and because of this ambiguity, us and several others went into the 2015 to try to resolve this issue, to try to align the R values and U factor table, and we're successful in doing so to make it so that it aligns so that there's not this discrepancy between the R values and U factors. Now, there still might be a couple, and it still might be in some places, but it's not near as bad as it once was. Okay. The total UA alternative. This is the language of the total UA alternative path. Basically, the idea is in the U factor table, it allows a certain amount of heat release in any given assembly. Okay, so much goes through your roof, so much goes through your fenestration, so much goes through your wall. Okay, the UA table, or UA total UA alternative, basically says we don't care what those percentages are, just as long as the total amount of energy that your house loses stays the same. So if I reduce the amount of energy that's lost through my windows, I can increase the amount of energy that's lost through my walls, or vice versa, or what other parts of the assembly components of the house. So as long as the total UA, which is U, which being the energy loss per square foot, times the A, being the area of that loss, remains constant for the entire house, you're okay. So this is in an equation form for those engineers like myself among us. So U reference, basically meaning the reference from the table, the U factor table, times the area of the assembly, which is your proposed house, and equals the U actual, your proposed U value, times the assembly area. And since the A assemblies are going to be equal, you're just basically trading off one U for another U. So we'll do an example here in a little bit.